Thank you, Dr. Alex, for your introduction. Very good morning, everyone. My name is Janaka. I am a postdoctoral researcher at SNT. Today, I'm going to share some of the highlights of our recently launched project on black mass processing. So in this presentation, I would like to mostly emphasize on the characterization and pre-treatment approaches and leaching approaches studies that we have done recently. So before going into the very technical things, I think it's important to get an idea about the black mass nature. So as you know already, the black mass is coming from as a result of the recycling process of lithium-ion batteries. So basically, this black mass contains lots of lithium, nickel, cobalt, and manganese, those kinds of critical minerals coming from the cathode electrode. And also it contains a significant amount of the graphite that's coming from the anode electrode. Of course, it contains some copper and aluminum foils. It's important to know this black mass contains also organic binders. The black mass actually, as I mentioned, is coming from the lithium-ion battery. Based on the metallic composition, the cathode can be categorized into mainly 5 or 6 categories like this. But in this study, we use the NMC black mass that contains high lithium, nickel, manganese, cobalt oxide. Based on the critical mineral ratios, we can have lots of grades of NMC black mass. So this is the process of recycling spent lithium-ion batteries. You can see black mass is actually resulted as a byproduct of these kinds of lengthy mechanical process. It's comprised with lots of shreddings, screenings, and different types of separation methods. So black mass appears in the color of black, and the particle size is very fine. And in this process, we can also get some aluminum and copper in a metallic powder form. So let's move into some highlights about our characterization. So this sample actually we obtained from the US Strategic Metals Company. This is the NMC type black mass that contains high nickel around 22%, and the lithium and the manganese is around 5%, and the cobalt is 7%. The challenging thing is that it contains a significant amount of graphite, around 40%, and the binders around 70%. So we have performed also some XRD analysis in order to identify the crystal phases here. So you can see the main critical metals, lithium, nickel, cobalt, and manganese, exist as a complex oxide, and the carbon exist as a separated graphite here. So before applying any hydrometallurgical techniques, we need to understand how these critical metals exist, what are the forms. So in this case, we need to know how to break down this complex oxide that will be amenable for the leaching process. And we have done some thermal stability analysis. You can see in our TG and DSC analysis there's some small mass reduction because of the moisture releasing temperature between 25 to 175 degrees. And also we observe another mass reduction due to the organic binder elimination, 250 to 600 degree. And there we observe a very significant mass reduction between 600 to 800 degrees. Actually, this because of the decomposition of the main lithium and critical metal oxide, and also some carbon release as the carbon dioxide. And we also measured the particle size using wet analyzing methods using the microtag, and we identified our black mass is mostly under 140 micrometer. So now let's move into some highlights related to the pre-treatment approaches. So we have attempted to separate some impurities using basic physical pre-treatment technologies such as some screening. So we use the dried black mass. Here you can see we separated the coarse particle over 300 micrometer. That basically contains a lot of copper and aluminum foils. And the fine particles less than 40 micrometer. In this section, we couldn't observe any copper and aluminum foils, and this is actually the majority of the black mass, that's representing 90% of the black mass weight. In order to understand more about the chemistry behind here, we have conducted some chemical composition analysis. So based on this, we identified between 500 to 300 micrometer. We observe lots of copper and also aluminum. And if you see the mass distribution between 500 to 300 micrometer, the mass fraction is very low, less than 10%. So if we separate the coarse particle over 300 micrometer, that is enabled to separate in 87% of copper and also 89% of aluminum, with nickel loss only 5%. So there's some potential for our future process optimization to remove out those kinds of copper and aluminum before applying any hydrometallurgical process. And also we tried with the thermal pre-treatment methods. So we for some tests, we have mixed some chemicals before introducing the black mass into thermal treatment. We varied the temperature and also we varied the retention time. You can see at the different temperatures, we got the black mass with different appearance. Basically, at a very high temperature, we observe the black mass turned into some hard type because some metallic oxide converted into metal form. And this is one of our key highlights here. We have tried with some pre-leaching tests in order to understand the impact of the thermal treatment. You can see if we introduce the black mass without any thermal treatment at room temperature, it generates a stable form. This stable form can actually diminish the leaching efficiency of the critical metals. But at the 350 to 450 degrees, when we apply that types of thermal treatment, we observe that we can avoid of this kind of stable form formation. And very high temperature, we observe some unstable bubble. Actually, that's because we assume because of the carbon dioxide emission. So our hypothesis is that during this temperature range, we could eliminate the binders and organic. That is the reason for avoiding these kinds of formation. But however, in order to get the verification about our idea, about our hypothesis, we have performed the XPS analysis. As you know, most of the binders are formed as PVDF. So we check the fluoride at the room temperature black mass and the 450-degree black mass. You can see the fluoride is significantly high at the room temperature, where it's significantly decreased when we increase the temperature. So this fluoride is actually related with the PVDF, and also some fluorides are connected with some critical metals such as lithium. So after the increase in the temperature, most of the PVDF eliminated, but still some small fluoride remain with that is associated with some critical metals. And also we perform some XRD analysis to evaluate the impact of the thermal pretreatment. You can see at the low temperature, basically the critical metals exit as a complex oxide here, and you can see the graphite. But when we increase the temperature, most of the metal oxide decompose into their relevant metal oxide, and some of the critical metals turn into the metallic form. And we observe the lithium mostly tends to exit as a lithium carbonate at a high temperature. So these kinds of change of the crystal phases that is really important, and this is have a high impact on changing the leaching efficiency of the downstream process of black mass. So now I'm moving into the leaching approaches. Here we tried with the different two types of routes. First one is about the bulk leaching. Actually, in the bulk leaching, we try to dissolve all the critical metals, lithium, nickel, and cobalt into the solution. And in the selective leaching, we targeted some specific critical metals dissolution. So this is the experimental setup that we use for our lab scale leaching, and we have measured the ORP and pH variation during each reaction. So after the leaching, we filtered, and you can see the filtrate color is a little bit dark green. That's basically coming because of the high nickel. So I will not share all the results about the leaching, just only some highlights about the bulk leaching. Here we tried with the different lixiviant. We tried to leach with the sulfuric acid and with sulfuric acid with sodium metabisulfite and with hydrogen peroxide at around the pH 1.5. You can see in all conditions, all kinds of lixiviant is the critical metals all dissolve more than 70%. Then we also try to optimize these leaching efficiencies regarding the sulfuric acid. So then we decrease the pH 1.5 to pH 0. You can see the cobalt, nickel, and manganese, those critical metals leaching efficiency increase over 90%. And we are still doing some tests to optimize this leaching condition. Our target is 99%. Now I will talk about some selective leaching results. You can see this is the results of selective lithium leaching. In this test, we use the black mass that thermally treated at 450 degrees. Here we use basically the water as our lixiviant. But the most important point is for the lithium selective leaching, we can control the ORP by introducing some reductant with the main lixiviant. If you remember the Port-Bay diagram related to the lithium, we can, if we decrease the ORP value under certain level, we can dissolve a lithium as a lithium ion. So here, with some reductant and the water, we observe we could achieve around more than 70% of lithium, while remaining other critical metals mostly in the leach residue. And also we tried with other types of selective leaching, specifically lithium and manganese. In this study, we used the black mass obtained from the thermal treatment at 900 degrees, and here we use some certain additives to change the crystal structure. So as a result, we observe more than 95% of lithium and manganese could be leached out at the pH around 1.5, where the most of the nickel and cobalt remain in the leach residue. So this is the conclusion part. Actually, I have pointed out the key takeaways at the each stages, so I don't want to repeat that. And we are preparing some publications, and we are targeting some patents. That's why I couldn't share some of the technical things. I think in the future we can share much more information. Actually, we are developing some process flow sheets targeting the different approaches. The first approach is NCM black mass processing, that is targeting the bulk leaching and removing the binders and graphite at the upstream. And our final target is making lithium as lithium carbonate and manganese nickel cobalt as sulfate. That is having the purity more than 99.9%. That is suited for the battery material. And this is actually we are developing based on our industrial experience. And this approach too, we are targeting the NNC black mass for some selective leaching. In this case, we try to separate out the aluminum and copper, that we could reduce some chemical costs on the downstream that's used for this kind of impurity removal. And by applying some different types of thermal treatment and selective leaching, we separate out graphite and also binders. Especially in case of manganese, some industries consider manganese is not that economical to produce for the battery material. So if we are going to consider this as a disposing thing, then this process is targeting making the lithium, nickel, and cobalt only, but reducing the chemical cost and the reducing the operation stages. I would like to acknowledge our sponsor, Missouri Department of Economic Development, and our industrial partner, US Strategic Metals, and our all the advisors. And I would like to thank our research group leading by Professor Lana Alaga, and we are doing also some other critical metal projects, so we are open for future collaboration. Thank you so much.
Okay. Thank you, Dr. Janaka.